I'm Leon Jackson. You've seen me in such fine quality chemistry videos as Solubility and Chemistry. Are they compatible? And Solubility, oh solubility, what would we do without you, solubility? Alright guys, on a more serious note, it's kind of early in the morning. I'm trying to get this done because then I got to make preparations, the final preparations for the field trip, for the science fair. Good luck to our players. Guys, I'm going to give you a quick overview of Chapter 16, looking at solubility and equilibria. Okay, and you don't have this slide on your Chapter 16 notes. I'm just going over it. Quick review of the Ksp. It's known as the solubility product constant. Again, think of it as an equilibrium, like we have been dealing with in the past few chapters. Okay, and the solubility product, the Ksp, that is the equilibrium constant when you're talking about a solid substance that's dissolving in a solution. Okay, an aqueous solution specifically. Okay, and the idea is how much, what level does the solute, what actually gets dissolved, dissolves in the solution. Now the higher that the Ksp value is, the more it dissolves. So there are some things out there that they dissolve, they barely dissolve, and there are other things that they dissolve fairly quickly, you know, like sugar and salt. Those dissolve fairly easily. But you know what? If you took a piece of styrofoam, like from a coffee cup, and you were to go and put it in water, yeah, we could be waiting a long time for it to do any kind of serious dissolving. Okay, but even then, for the most insoluble of salts, they still dissolve, but there is some kind of an equilibrium, you know, I whip my head back and forth. Yeah, that kind of thing. Now, you guys are getting a problem set, okay, that deals with Ksp. Now, I'm really touching on three main things. We're going to look at solving Ksp when you have the molar solubility. We're going to have the Ksp from the gram per 100 milliliter solubility, and then of course looking at the Ksp when they give you the pH. So there are three ways to look at this. Now on the worksheet that you guys are getting, you are going to have some problems that you're going to be working on a separate sheet of paper, but the example is done step by step, which you find in this particular chapter, guys. There's a lot of examples done step by step. Okay, so for example here, when we talk about write the expression for Ksp, okay, for silver chromate and calcium phosphate. Okay, at this point here, for something like this, for silver chromate, this is where you guys are going to need to know what are your, how does it break down? What are those oxidation values? Okay, those oxidation numbers, because remember, if this breaks apart, you're going to get two silvers and one chromate. Okay, with the silver each having a +1 charge, and the chromate has a -2 charge to it. So when we look at the Ksp, we look at the concentrations, because remember, in equilibrium, it's all about the concentrations. So you get, here's silver, here's the chromate, you multiply them together. Hey, it's just like we did in the previous chapter, and you get that's 2 there, that's squared, the Ag is squared. You say, well, wait a minute, why is it squared? That's because we've got 2 of these. That's why. So remember, it's the basic, we got, I don't know, it was like chapter 14 that we started to talk about equilibrium and the basic formula that the K of whatever is equal to the concentration of the products to the nth power divided by the concentration of the reactants to the O power, that kind of thing. Okay, and that's what we got here. So our Ksp, when we write the expression, is equal to the concentration of silver squared times the concentration of the chromate. When we look at calcium phosphate, on the other hand, we know we've got 3 calciums and 2 phosphates. So again, you got calcium here to the 3rd because there's 3 calciums, and then the PO4 squared because we have 2 phosphates. Now, somebody might be sitting there thinking, wait a minute, you're trying to be a trickster here. Wake up, Watkins. What about this part? Can you riddle me that, Patrick? What about the solid? Well, that's just it. Because the solid is considered insoluble, it's not included. That's the beauty of it. Okay? Which is why for the KSP, you're not going to see the solid in there. You are going to see the parts that make up the solid. Okay? Products over reactants. But the reactants, in this case, they are not dissolving, so they don't count. That's why. Okay. So again, you write the expression for the solubility product constant for calcium fluoride. Well, here's CaF2. Now, on the exam, they will, this should already be balanced out. They're not going to try to trick you for stuff like that. Okay? So in this case here, again, Ca with the 2 plus, and then the F, the 2F with the minus. Okay? And again, Ca, concentration of the Ca2 plus with the F. Wake up, not this! Okay, so you're going to have the calcium and the fluorine. The calcium's not squared because it's only 1, but you have 2 fluorines, so you have to square it. And once again, I would like to point out, Frank! The CaF2 is a solid. It doesn't dissolve. Okay? So it's not figuring into the thing. MgASO42, magnesium arsenate. Oh, that is just something I want to chomp my teeth into. Okay, it has a solubility of 1.6 times 10 to the minus third grams for every 100 grams of water. What is the KSP for this compound? Okay, I would like to point out that I do have a number of examples in this chapter already worked out. That's why you guys have it in 2 slides. Oh, it's not this paper. 2 slides per page. Okay, I'm trying to pay attention to my timing here. 2 slides per page, so it's a little bit bigger, so that you should be able to see the whole thing. Okay, lots! All right. So, in this case here, let's go ahead and look at it. We can use the molar mass of magnesium arsenate to calculate the concentration, because they gave us, notice how they gave us the grams for every 100 grams of water. Now, okay, for the grams, we can change that easily to moles. That wouldn't be that hard, because you figure out the grams to moles. Basic chemistry, yo. Now, what about that 100 grams of water? How in the world do we change that into a volume? That's where that density thing comes in. That's where it comes in. Okay? Well, what's the density? Oh, gosh, let me see, Yeah, it's 1 gram per cubic centimeter, or 1 gram per milliliter. Yeah, so that's basically it. So we can easily change this. If this is 100 grams, hey, we can change it to 100 milliliters. Oh, that's so hard. So once you have that, now you can figure out your molar concentration, Patrick. Yes, I'm laying it down good and thick. This is a step-by-step. Then the next trick is to figure out how is it going to break apart when it dissolves. Now, for these ionic compounds, I would say to you guys that they are pretty much you can know where the line is going to break, okay? You're going to have your cation typically in the front, not 100% of the time. Remember cation? Ram? You remember. You do. All right. So then after that, once you figured that out, then you can figure, hey, for every mole of solid that's been dissolved, you get 3 moles of magnesium and 2 moles of arsenate. So we can go ahead and multiply those out here, and we can get ourselves that nice, wonderful, lovely concentrations that we have. You have to multiply because of the ratios. This is like, if you look at a car and you want to break it apart, that you get the steering wheel and the tires. Well, if I have 1 car, I got 1 steering wheel, 4 tires. If I have 5 cars that are breaking down, I'm going to have 5 steering wheels and 20 tires. Okay? Alex! All right. This one, I don't have the solution here for you on the paper. You'll have to work on that one, but you have the technique already. You have the molar solubility in a 0.1 molar Na2SO4. This value here, this is a typo. This should be an Na2, so you need to change that, okay? That you guys see that. This number, I am not sure how in the world that got in there. It's a typo, you can ignore it. I wouldn't worry about it. Okay. So, in here we have a saturated solution of NgOH2 in contact with undissolved solids prepared, okay, at 25 Celsius. Now, I want to point something out about the Ksp. The only way the Ksp changes if you change the temperature. Now, stop and think about it. If you change the temperature, you're going to change how fast the thing is going to dissolve, right? Because when something dissolves, what does it take to break down something? Energy. And typically, the idea is you'd get the energy in the form of heat. Samuel! Okay? So, it does take heat energy to help overcome the bonds of attraction that they have, and then they break. And then you can go from there. Alright? Okay, I do need to move on here. So, again, this is another grams per liter. This is another grams per liter type problem. You'd say, but wait a minute, you only have it. Remember, even though on the worksheet that I gave you guys, where you go grams for, based off of molar solubility, or I go grams per 100 milliliters of solubility, remember, you got grams per liter, so you know what? You can probably go with the grams per 100 milliliter of solubility. Just remember, you've got 1,000 milliliters to a liter. Okay, that's all you need to do for that. Let's see, what else do I have here? Okay, that I'm going to move on. That was part of solving the problem. Okay, of course, here's the thing. Yes, you can use to calculate the equilibrium concentration of another ion if you know the concentration of the other. This is kind of like Captain Obvious is here. But, you know, just one of those things, it's just a little thing to pick up as we go through. Now, when you go and look at this table, these are all kinds of solubility product constants at 25 Celsius. They love to choose it at 25. Seems to be a standard that they have, but I want to point out to you guys, that this is by no means all of it. It's not all the goods, okay? But it is quite a few, and you can see all the different things they break. And notice how they break it off based off of the anion, you know, that negatively charged ion. The acetates, the bromides, the carbonates, the chlorides, the chromates, the fluorides, the hydroxides, the iodides, the phosphates, and the sulfates. Susie! Hey, I gotta be fair between the guys and the ladies. Okay? So again, these are other questions for you guys. And again, here we're looking at calcium phosphate. It's a water-insoluble mineral. Oh, well, that's an interesting one. What does that mean when they say water-insoluble? Think about it. If something is soluble, we know that it can break down. It can be dissolved. If something is insoluble, that means it doesn't break down. In this case here, it's water insoluble, which that tells us, hey, when it's in water, it doesn't break down. Now, I got to point something out. It doesn't mean that it's never, ever, ever, ever going to break down, ever. That's not true. It may be breaking down just such a tiny, tiny bit. Kind of like USC's football chances against UCLA next season. Oh, yeah. So just a little bit, just tiny, okay? oops. Let's move on here. And again, it shows you how to go ahead and work on that. Okay, how to put that through. I'm trying to go through, calculate the molar solubility. Okay, so we're going to go ahead and I am going to so for this one here, you got two situations where you're looking at the molar solubility of calcium fluoride in a solution that contains 0.1 molar of calcium nitrate. Okay, that's one thing. That's one situation. And then the second situation is in 0.01 molar of sodium fluoride. Whew, man, this sounds very exciting. And this just gives you guys the very fast way of doing this. And I'm going to keep going because I'm running out of time. Okay. Come on. Okay. That one we'll have to talk about perhaps a little bit later. I'm not going to be able to do that this morning with you guys. Okay. But again, this one, they do go into an explanation about which ones they dissolve. More soluble and acidic as opposed to a basic solution. Okay. And again, part of it, you may not necessarily be able to tell based off of looking at the thing, looking at the, wait, try that again. Looking at the formulas, okay? But, let's see. Guys, at this point, I'm going to have to stop. I am running out of time and trying to keep this bad boy under 20 minutes. So I've given you the thing. I'm going to see about getting you guys the Chapter 17 notes this morning as well, so you have that over the weekend. That's when we get to work with a little bit of thermodynamics, where we get to work with the Gibbs free energy. You AP biology people, you should know about the Gibbs free energy. Yeah. And we're going to be working on entropy, otherwise known as chaos. Okay, which John here knows everything about chaos, right, John? Okay, so I'll give you guys the Chapter 17 notes for that. You're going to be working with Gibbs free energy, spontaneity, okay, things like that. And if you don't know what spontaneity is, you've seen me do this the entire video where I randomly called out people's names. Okay, trying to tell people to either wake up or pay attention or whatever it is possibly. Okay, I will see you guys later. I will see you guys on Tuesday. At that point, this assignment, you should be able to do it on paper. You can do this on a separate sheet of paper and turn that into me on Tuesday. That will be the homework, okay? Because I've got Chapter 17, Chapter 18 to go over with you guys. They're relatively short. Excuse me. I'm going to give you guys some problems dealing with those two chapters. And then there's one last thing, photoelectron spectroscopy. Okay, that one I got to spend a little bit of time working on because it's really, really visual. And it's almost a guarantee that it's going to be on the AP exam. So, have a good weekend, guys, and take care. Not this!